This lecture is going to cover balancing chemical equations. Oftentimes students struggle a little bit with this the most, and that's because there's a couple of things happening. First of all, this is a whole new concept, but you have to remember that because of conservation of mass, mass is neither created nor destroyed, meaning poof, we just don't come up with mass, or poof, it just magically goes away. It's always there in some way, shape, or form. And in addition to that, we're looking at these chemical reactions, these chemical equations, and you have to remember always that if I have in a beaker, here's my beaker. Well, I'll make this a vessel of some kind with a lid because we're talking about gases. I have billions and billions of these butanes in this beaker. They're all over the place. Okay, all over. As soon as I add oxygen gas with heat, all of these butanes are reacting. What we're showing with a chemical reaction is just one example of what one butane is doing. So because of conservation of mass, this chemical reaction is simply showing one example. So when we balance chemical equations, I'm going to start with combustion because combustion is simply the easiest because it has three simple rules. Okay? In order to balance combustion reactions, you know this is a combustion reaction because it is some hydrocarbon, some carbon-hydrogen entity added to oxygen gas with heat. Okay, triangle represents heat. Again, combustion, blowing things up. Always gives us carbon dioxide and water as our products. And by the way, this L should actually be a G because it's with heat. And if it's with heat, that means the water will not be a liquid, it will be a vapor. So the rules for balancing combustion reactions, the easiest one there is to first and foremost balance all carbons first, ignoring everything else. So when I say balance it, what I mean is I want to have the exact same number of things on both the left and the right side of the arrow. So on the left side of the arrow, in the reactant position, I have 4 carbons. I know I have 4 carbons because that's what my subscript tells me. On the right side of the arrow, I only have 1 carbon. So I'm going to use the coefficient of 4 so that I can say my carbons are equal. Now, my second step is going to be to balance all hydrogens, ignoring everything else. So on the left side of the reaction, I have 10 hydrogens. Hold on, I wanted to change colors there and it didn't work. I have 10 hydrogens because that's what my subscript tells me. On the right side of the reaction, I have 2. So in order to make the same amount, I'm going to use a 5 as a coefficient in front of that hydrogen. Because when I have H2, that's what it looks like. Okay, when I have H2, now I'm going to say I have 5 of these. If I count all the H's, excuse me, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That now means all of my hydrogens on both the left and the right side of the equation are equal, 10 and 10. So basically we're just multiplying the subscript by the superscript. I said superscript. I meant to say coefficient. I apologize. Third rule is to balance the oxygens. This is the last step because the oxygens are much easier to balance. It's the only element within this chemical reaction where if I put a coefficient here, it will not affect the amount of carbons or hydrogens. So what I need to do is I need to think about how many oxygens I have on the right-hand side. Now, I want you to pay close attention to this. We put that 5 coefficient in front of the water. That gave us 10 hydrogens. Much like if we were to say, oh gosh, I don't know, 3 parentheses x plus 2. Much like that 3 applies to both the x and the 2, this 5 applies to both the hydrogen and the oxygen. So I have 5 oxygen on the left-hand side and 2 oxygen on the right-hand side. Now, normally we'd say, well, gosh, what are we going to do? That's a little complicated there. You know, you got to play with numbers and find the right coefficient. But if I add something to the water, then that's going to mess up my hydrogens. So the rule here is if you have odd number of oxygens on the right, then we take that number and we divide it by 2 as the coefficient on the left-hand side. So this becomes the coefficient on the left-hand side. Okay, so what do I mean? I have 5 oxygens on the right. That's an odd number. So I'm going to put 5 over 2 as my coefficient in front of my O2. Why can I do this? I can do this for one mathematical reason. If I were to say, for example, 1 over 2, yes, we know that as a half, right? But what if I said I had 1/2 of O2? Okay, let me just say this one more different way. 1/2 of an oxygen bonded to an oxygen. What that really means is 1 oxygen. So in the same way, 5 over 2 oxygens means that those 2's cancel out. It's just a quick mathematical trick in order to easily and efficiently balance combustion equations. So now that I have that, and these are my rules, I can't leave a fraction as a coefficient. We always need to have whole numbers as a coefficient. Because of this, the easy way out is to get rid of the fraction just like we do mathematically with anything else. So I'm going to take this whole entire equation and multiply it by 2 so I can get rid of that fraction. And this 2 will apply to every single compound in the reaction. So I will wind up with 2CH4H10. I'm going to ignore writing the states for just a moment. 5O2 yields, let's see, 8 CO2, because 2 times 4 is 8, plus 10 H2O. Now, if you go and count up all of the individual elements on the left and the right, so let's do that. Carbon, hydrogen, oxygen, carbon, hydrogen, oxygen, okay? Now, if I count them all up, I'm going to find that I have exactly the same thing. I don't know why I wrote what I wrote. Let me just fix that right quick. I have a little bit of an error. Again, can't write and talk. Apologize in advance. All right, so what we have here is on the left-hand side for carbons, that 2 applies to C4, so there's a total of 8 carbons, and here I have 8 carbons. My 2 also applies to my hydrogen, so that means 20 carbons, because there is 10 times 2. And I got the same thing going on here, 10 times 2, so 20 carbons. Then finally, I have 10 oxygens and 10 oxygens. You will note that these are all the same. So I have a balanced chemical equation because all the same elements on the left and the right-hand side of the arrow are balanced. They have the exact same number left and right. Here, if I'm looking at this, what I'm going to show you is just a little bit different way to write some stuff to make it easier, and a little bit different way to think about things, again, just to make it a little bit easier to see. You will note that the first and second chemical reactions here are exactly the same, save for one difference. The one difference is that I've written water as HOH instead of H2O. I do this so that I can easily and quickly see how to balance and recognize the hydroxides. So when I'm looking here, everything that's in a parentheses, or not in a parentheses, but similar, needs to be maintained. And what I mean by that is you have a polyatomic here, which by now you should be able to recognize. Those are polyatomics. This is a polyatomic, okay? If I balance the polyatomics as a whole, it's much easier to see. So the way I just kind of sort of represent this in a generic kind of way is saying it doesn't matter what my polyatomic is. I could replace it with anything, but just so I could visually see what's happening, I have to kind of look at it a little bit differently. So here, for example, I have barium, and I'm going to switch this up, and you're going to laugh when I do this, but that's okay. Okay, you can easily see that I have 2 hearts on the left and 1 heart on the right. That heart, generically, sillily, represents hydroxides. I could do the same thing with the perchloric acid. So I could say, all right, let's try this a different way. Okay, my stars now represent the perchlorate. So what does that mean? You can easily see that I have 4 stars on the left and 2 stars on the right. Okay, so when we balance some of the entities as a whole, it just makes it much easier to see. So now, if I go ahead and look, I'm going to start balancing with just the chlorates because they seem to be the most complicated and have the most number of things. Remember my stars and hearts. I don't want you to confuse them. This 2 does not apply to this 4 here. Okay, it does not apply. They're not related because remember, the 4 is attached to that perchlorate, and that perchlorate is a whole entire entity in and of itself. All I'm saying is that this barium, in some way, shape, or form, has 2 perchlorates attached to it. Yes, I wrote that backwards, and it's okay. Okay, so I don't mean there's 8 oxygen. Well, technically there kind of is, but not 8 oxygens attached. It's simply 2 perchlorates that are attached. The whole thing in parentheses. All right, so now let's start with the perchlorates. I have 1 perchlorate on the left and 2 perchlorates on the right. So if I throw a 2 in front of this perchloric acid, it's understood there's a parentheses here that we don't write because there's only 1 perchlorate, and that 2 applies to both of them. Oh, and by the way, now, once I've put in my first coefficient, I like to see whatever's attached. So that 2 attached, or that 2 coefficient applied to the perchlorate, which also gave me 2 hydrogen. So if I have 2 hydrogen here, well, gosh, over here, I only have 1 hydrogen. So if I throw a 2 in front of it, now I have 2 hydrogens, okay? Well, that 2 in front of the HOH applied also to that understood hydroxide. If I have 2 hydroxide over there, oh wait, I already have 2 hydroxides over here. So we're good. The hydroxides are good. And I can look and see I have 1 barium and 1 barium, so everything is good and everything is balanced. When I start with one thing and work each element in there to lead me to the next one, it often has a tendency to just work out the way it should. Answer to that. So I guess we are going to work this one. Okay, so if I balance all the carbons first, I'm going to put a 4 out here because I have 4 carbons. Now I got 4 carbons. Now I'm going to balance all the hydrogens, ignoring everything else. I have 8 hydrogens here, 2 here. So if I put a 4 out front, then I have 8 and 8. Now we're going to deal with the hydrogens. Your carbon dioxide, that 4 applies to both the carbon and the oxygen. Okay, so I have 8. And then here, I have 4, so that's a total of 12. Over here, I have 2, and then 2. So what number times 2 plus 2 gives me 12? The answer should be 5. Okay, if I put a 5 in front of that O2, then what I have is 5 times 2 is 10. I got the 2 here. 10 plus 2 does in fact equal 12, and I'm balanced.